So good afternoon, good morning, everybody. Let me start by thanking Alex, Alessandro, and Carlos for setting up the meeting and ICT Star for the support. So the story I will tell you about today, it's slightly complementary to what has been discussed in the previous session. And in particular, we'll be dealing with concepts such as quantum simulation applied to problems related to nuclear physics, and in particular applied to gauge theories. And I've chosen, given the fact that ICT Star is the Nuclear Physics Institute, I've chosen a kind of an unconventional route to present some of our recent, but also less recent results, which instead of going from abelian, which is typically the simplest thing, to non-abelian, it does the opposite. However, the justification because of that, you will see in a moment, is methodological. In particular, I've changed the title and I've introduced this encoding route, and I will explain to you later on what this encoding does mean and why it is very functional to realize physical phenomena that are very close to nuclear physics. And before really starting, let me acknowledge my collaborators, and in particular, Enrique Ortega from Bilbao, Debashish Banerjee, at the time in Bern, and Federica Sucharase in Trieste, as the people that really had the main ideas on these topics. So the outline is the following. I will first give you a brief panoramic of what analog simulation for gauge theories means and what is the current status, very briefly. And I will then show you what is the main issue, which is how we deal with the gauge invariance and how we can somehow circumvent this issue by applying encoding strategies that for some of you, especially in the computational physics community, they will be very familiar. You will see later on. And then I will show you two examples. The first example historically to which we applied these techniques is So3 models. And I will show how these So3 models can be realized also with cold atoms in optical lattices, in particular mixtures of atoms. And later on, if time allows, I will also show you how this encoding strategy can be applied to abelian theories. And in fact, they have already been applied in experiments. And they have already at the boundary of what we can do with classical computers. So let me start with the motivation of the challenge. I think many in the audience are probably even more familiar to the challenges than I am. So tackling gauge theories is not only of pivotal importance, and there are also simulations which are somehow fundamentally challenging. So situation where the sign problem occurs. So we cannot use conventional sampling techniques such as Monte Carlo methods. And here you see depicted two examples we have already seen this morning in the first talk, the phase diagram of quantum chromodynamics. And we know that, doing simulations when the baryon-chemical potential is zero, which is around this vertical line, is relative. It's not simple, but it's feasible. Instead, exploring especially large region where the chemical potential is large, it's very challenging because Monte Carlo cannot really be applied because of sign problem. And similarly, real time-dependent processes are also very challenging because the Kelly's action becomes problematic, complex in general, and sampling cannot be performed. Okay? So there are two clear goals in the eyes of people coming from the quantum simulation community. One is real-time dynamics and the one is really finite density. So what is the panorama, the current panorama of quantum simulators for nuclear physics and high energy? So I will say that there are different levels of models, implementations, and also goals. In terms of models, we have already heard about unitary Fermi gases. I'm mostly interested instead, not really in effective model, but ab initio models, so really thinking about gauge theories. In terms of techniques and strategies, there are many on the market, ranging from analog, digital, and hybrid. I will be mostly focusing on this analog. I will tell you in the next slide for those who are not familiar what this really means. And of course, the outputs, one can see that the outputs level on different complexities. First one, maybe more qualitative, is to introduce new perspective and interfaces between the different fields without really solving a question that is either specific to nuclear physics or quantitative. And then there are, of course, qualitative and quantitative insights on established problems. So what is analog simulator in a nutshell? The basic idea is that we are interested in a problem, and let me just focus on Hamiltonian problems, where we have given operator H that we decompose into many operators. And what we do in analog simulations, we try to perform a mapping of this original problem, which is possibly exact, into microscopic degrees of freedom that we control, okay? That we control by means of external field, like atoms in optical lattices, or trapped ions, or circuit QD, and so on and so forth. And then on top of these systems, of course, is not only do we realize the dynamics, we need to have proper probing tools and protocols, like, for instance, state preparation, and we have to have an understanding of the error that we commit when we perform this procedure. Okay? And at the very end, once we have this theoretical understanding, we go talk to the experimentalist and see whether this is ultimately feasible or not. So if you want, this is on the right, you can see an example of a classical analog simulator like wind tunnel. Okay? So we are doing more or less the same, but quantum mechanically. And the challenges, which are very typical, are initial state preparation, probing, validation, and so on and so forth. Okay, some of these challenges are not fundamentally characterizing nuclear physics or energy problem. They are also characterizing more conventional in the field, at least condensed matter issues. While there are some very specific challenges for high energy physics and nuclear physics problem, which I underlined here on the blue side, which are particularly hard to achieve. And in particular, I want to emphasize this engineering the desired dynamics. So having this type of theories in the lab, it's very challenging. So from the point of view of gauge theories, the science is very simple. It is very hard to realize a gauge symmetry, so to really engineer gauge invariance. And this actually required a shift in the field. Instead of thinking about Hamiltonian engineering, thinking about symmetry engineering. Instead of focusing really on the microscopic processes, one is interested in realizing the dynamics, which, for instance, in the case of Hamiltonian formulation, spans only a given part of the Hilbert space. So there has been a lot of works in this field, starting from early 2000s, actually, very first proposals, and then I would say the field really started progressing a bit faster in 2012, 2013. And there are a lot of people that work on that. Sorry, this is an incomplete list. I apologize for missing some of you. And these are nice reviews that I find very informative. And in particular, if you are more familiar from the energy physics side, I would really strongly suggest this first one by Uwe Jens Wiese and the second one by Preskill, that give a particular overview on the topic. And let me also mention, of course, that Zore's talk later today will cover also some of these, in particular in the context of ions, ions. So now I want to, this is kind of a panoramic of this analog simulation. Let me go to the point of how we deal with gauge invariance. Okay? So in particular, what we started looking at a few years ago was the following. We wanted to formulate a model that shows interesting feature connected to nuclear physics. For instance, I think about chiral symmetry breaking, or the existence of bound states, and so on and so forth. And also at the same time can be realized utilizing simple two-body interactions. Okay, and the ideas that we had in mind at the time was that there were experiments both in magnetic atoms, but also in cold mixtures that were realizing this exotic or generalized Heisenberg model, and we were wondering whether we can formulate a model that has the correct features and then is also realizable experimentally. And what we did, we formulated a gauge theory, and I will explain to you the challenges in realizing this kind of gauge invariant dynamics already with this specific model. And what we had is a So3 gauge theory. Okay? And in particular, we utilize a formulation which is so-called quantum link formulation. I don't want to go very much into detail, but the basic idea is that instead of utilizing continuous variable parallel transporters to represent the gauge fields, we utilize simpler operators that are maybe more accessible in the lab. So the model that we had, in particular, is defined by this Hamiltonian here. And you can see this is the lattice, is a one-dimensional lattice. And in this one-dimensional lattice, we have two types of the degrees of freedom. On the vertices, which are denoted by these empty circles, we have fermions. And the fermions can have three colors indexed by this letter A, 1, 2, and 3. So you can have double occupancies, triple occupancies, and so on and so forth of these fermions, and they can come in these three colors. to represent the gauge field, we choose spin 1/2 variables. So you can see them here in the bonds. Each bond has 2 variables, one gauge field on the left, one gauge field on the right. Look, I mean, actually, the right and left are referred to the vertex, sorry. Okay? So this is the notation. So if you take the bond between x and x+1, there will be the vertex xr and x+1 left. And these are just spin 1/2 Pauli matrices. And the first term in the Hamiltonian, which I denote here with this kind of orange box, is a term that describes the, if you want, the minimal coupling, so the tunneling of fermions mediated by the gauge fields. You can note that if you take the first 2 operator, this is like a color singlet on the left, and the second 2 operator is a color singlet on the right. The second operator that you find in this Hamiltonian is denoted by this blue area here. It's an interaction between 2 nearest neighbors, and you will see later on why we need that. And finally, there is a last term, which is this Gn squared. This Gn squared is nothing but a 4 Fermi coupling. It's essentially a local interaction between the different quarks. This theory. Now, the first thing that we did once we formed this model, we tried to work out what is the gauge invariant Hilbert space, because our goal in quantum simulation is to explore only the states which are, if you want, living in the same super selection sector. So it's, I mean, keeping gauge invariance is extremely important. And it turns out that while if you think about the total number of states on a single bond, you will think, okay, there are 2 states on the Pauli left on the right, 2 Pauli on the left. So there's already 4 states for the gauge field. Then there are 2 to the 3 fermionic sites. So this will be 32. Actually, it turns out that the only gauge invariant states are 4. Okay? So the local dimension of the Hilbert space on a single vertex plus the 2 bonds nearby, it's 4. And one can write down this combination in a particular manner. And it turns out that these combinations are actually labeled by m, which is the number of quarks at the given site. So there will be m equal to 3, m equal to 2, m equal to 1, m equal to 0. And they are unique states up to gauge transformations. And their microscopic formulas are pretty complicated. I spare you. They're not particularly insightful, I have to say. So the real point here is that if we have this complicated SO3 theory, we have an equally complicated Hilbert space. However, the effective theory, so really is actually acting on an Hilbert space, which is 4 sides per link, which is the same Hilbert space that the spin tree of Heisenberg model spans. Okay? So maybe there is hope of having some connection between this gauge theory and Heisenberg models. However, first of all, I mean, since we have formulated a theory kind of this not so common quantum information, the first thing we want to check whether the physics that this theory describes is interesting. So we want to have a look at the phase diagram, and this is what we did. And we did that utilizing numerical simulations, combining exact diagonalization for small system sizes and then tensor network simulations up to a given number of sites that allow us to perform relatively good extrapolations. And this is a cartoon of the phase diagram as a function of G, which is this 4 Fermi coupling from negative, so attractive, to positive, repulsive, and V. And again, V is positive on the upper side and negative on the lower side. Now you see, first of all, that there is a white region here, which is phase separation. I mean, this region was not immediately interesting for us, even though it could also be somehow explored, but I will keep it for discussions. And then what you see in this phase diagram are 4 phases in this shaded area, separated both by lines. The lines are analytical calculations, and by boxes, which are approximate numerical position for these transitions. And these different phases have different properties, and I will just like to illustrate some of these properties to you. I mean, the first thing that we studied is chiral symmetry. So we wanted to ask the following, I mean, can this model support chiral symmetry breaking? And chiral symmetry in this specific model, since we are using something which is very closely related to staggered fermions, they are nothing but translations by one-lattice spacing. Okay, this is the action of chiral symmetry on our model. And what we did, we computed, for instance, the scaling of the gap between 2 different states belonging to the ground state manifold, in case there are degeneracies. And we know if the chiral symmetry Z2 is broken, like if you want similar to a Hansen model, the gap between the ground state and the first low-lying state has to scale exponentially to 0 as a function of the volume of the system. And here you can see different regions here for very small values of this parameter rho, which is, I mean, is something that relates to the number of defects in the system. We should really be looking at this rho equal to 0. One can see that for the point denoted by this orange dot, which is in the middle of this phase, the gap clearly closes exponentially as a function of system size. Okay? So there are regions in this phase diagram which show this kind of symmetry breaking. These are both the regions on the kind of red and green. And these are the two important regions. Notice that both regions require finite value of V. That's why I've put this exotic for Fermi coupling and nearest neighbors. I mean, otherwise, it's impossible to get kind of symmetry breaking, apparently. Then another feature that we wanted to check, it's maybe a bit less typical of nuclear physics, but it's something that spurred our interest because there were at that time discussions about conformal windows in non-abelian gauge theories and so on and so forth. So we wanted to see whether these models actually support a finite stable conformal phase. And it turns out that this phase exists. It's denoted here in brown. In particular, it's a conformal field theory with central charge 1. And I don't want to enter into the details of that, but how we probe that. So what we did, we computed several things like two-body correlation functions and so on and so forth. One thing that was extremely simple to compute to demonstrate that this phase is conformal is the entropy of the system, the entanglement entropy. So what we did, we took these chains and then divided them into two, and then checked whether the entropy of a partition with respect to the other was increasing where we were increasing the length of the partition. And it is known that if you have a conformal field theory which is defined on a lattice of length L and a partition of length small l, this entanglement entropy should scale with this logarithm of the core distance. So this is old prediction by Olsey and then found again on the final lattices by Calabrese and Cardi. And these are numerical simulations done with tensor networks on simulations on this model, and for a couple of points. And in particular, the point that I want to show you is the one denoted in blue inside this phase. And this is described by the points line on this straight black line here. And all these points essentially sitting on a line tells us that the central charge of the system is compatible with 1, which is this C equal to 0.9983 and so on and so forth. While instead, if you move away from that phase, like these violet points and these green ones, which are outside of this phase, actually, the central charge. Well, the system does not show even this log phase. You cannot even define a central charge, of course. Okay. So this was the connection, I mean, potentially beyond X, but I don't want to make more comments on that also because the connection is a bit sketchy. So we had a complete phase diagram of this theory. It was kind of interesting for us. We also studied the presence of bound states. And in particular, we found that there are some phases where there are interesting bound states of more than one particle, in particular this red phase here. If you're interested, I can tell you a bit more. And then we say, okay, that's interesting. We have an interesting model, which is covers symmetry breaking, has some baryon-like physics, as a stable conformal window. So now it may be worth to see whether we can realize this experimentally. And what we did, we came back to the gauge invariant Hilbert space. Then we wrote out all the possible 4 states that I was mentioning you before. And then we said, can we simplify them? Can we simplify this picture and make it really equivalent to a spin 3/2 model? And the idea is that you can define that. You can do that. You can define spin operators, which are depicted with these cartoons. And when I have essentially 3 quarks here, I define a spin operator which is up. When I have 2, spin operator is up, but it's not plus 3/2, so the maximum spin operator of a spin 3/2, but is 1/2. If you have just 1, it will be minus 1/2. If you have 0, it will be minus 3/2, and you can write this in formula, and you can even write down something more. You can take down constituent quarks operators, which are a combination of the gauge fields and the fermions, and write down them as spin operators. Okay? So we essentially found out that there is a full one-to-one mapping between the local Hilbert space of this gauge theory and the local Hilbert space of spin 3/2. Okay? And the only thing that was maybe a bit more complicated was to determine, okay, where is this Fermi statistics coming from? Well, the idea is that when we were performing this mapping, we utilized a sort of Jordan-Wigner string, So we were attaching to each fermionic operators a string of number operators. It's pretty straightforward, but it's important thing to note, because if you compute correlations, you have to take care of that. Okay. Well, the point
Marcello,
is, yes?
5 minutes left. Sorry to interrupt, 5 minutes.
No problem. Okay, thanks. So then we said, okay, we have this mapping between this gauge theory and this simple Hilbert space. Well, what happens to the Hamiltonian? Because maybe the mapping will just make the Hamiltonian a mess. Well, it turns out that this is actually not true. If you work out the mapping carefully, the Hamiltonian looks like very much a Heisenberg model. So this is the first term will be just a spin exchange, Heisenberg spin exchange. The second term will be what is called an isotropic term, and then the fourth term will be a bit strange. But people in magnetism actually have studied that. It's called single ion anisotropy. So somehow this Hamiltonian is kind of, well, I would say not known, because there's been a lot studied, especially for spin one, but it's something which is not so crazy. And then we said, okay, well, we know now how we can implement that with cold atoms, and we developed two techniques. The first technique is actually not developed by us, but is inspired by other experiments and adapted by us, is to utilize Bose mixtures in optical lattices. So if you take mixture of two atoms, like denoted here by these yellow and blue circles, and you enforce the occupation of 3 atoms per site on a Mott insulator, kind of. Well, what you will see is that essentially you are defining a spin 3/2 system, utilizing Schwinger, utilizing the Schwinger representation, and the natural interaction that you will get is actually exactly the Hamiltonian that we are describing. Okay, so somehow these Bose mixtures find naturally these SO3 gauge theories. There is, however, an alternative platform, which I find also extremely interesting, is magnetic atoms of fermions, because you have to have odd spins. And in particular, we found that if you utilize this dysprosium of erbium in combination with quadratic Zeeman shifts, you can actually realize spin 3/2 models with slightly offset coefficients, which, however, do not really influence the universal properties of the phase diagonal. So, and there could also be other systems, but these are the two systems where we have things right under control. And what can we observe once we perform these experiments? Well, the idea is that one can, for instance, think about detecting chiral symmetry breaking, measure the equivalent of a chiral condensed fraction. And this turned out to be relatively straightforward, because this chiral condensed fraction maps into a staggered spin magnetization that we know can be measured with techniques that are familiar in quantum optics, and in particular one that came to our mind is so-called band mapping. If you are not an expert, just take this for granted, but this is mostly for the people interested in experiments. We know how to measure these things. Okay, I think essentially I am done with the non-abelian part. I will just tell you very flashy what we did on the abelian side. And on the abelian side, what we did, we tried to show an equivalence between what are experiments based on Rydberg atoms in optical tweezers performed both in Misha Lukin's group and Antoine Brouvet's group, and string dynamics in particular in the context of a Schwinger model. And I will not show you any formulas, also because I don't have time. But the idea is that when we realized that this mapping was correct, it was not only a quantum simulation of a gauge theory, but it was also something that allowed us to understand the non-equilibrium dynamics of observing these experiments in a kind of a false vacuum decay thing. And actually, it was not, truly speaking, a false vacuum decay, was more something like a string inversion. And this explained very nicely with simple quantum field theories the experiments that were performed at Harvard, where they observe a kind of a very exotic slow dynamics that is not typical in spin models, while instead it was known already in the context of a Schwinger model that you can have the equivalent of plasma oscillations if you want. So that's, I think, all I could tell you. Just let me recap. I show you that in these quantum simulators, we can try this encoding route. Instead of writing down theories full-fledged and try to realize them experimentally, we can encode some of them, so partially solve them, work directly in the gauge invariant Hilbert space. And this is convenient for non-abelian theories. I've shown you in this SO3 example. And it's also convenient for abelian theories in specific context. And in particular, we have found out that this is convenient for a Schwinger model. There are, of course, open points. This encoding strategy will not work in general. And in particular in 2D, it's not so easy. I mean, now we have some results in abelian case, but in non-abelian, we have no idea. And also for other non-abelian groups, it is considerably more challenging than SO3 for reasons related to the fact that SO3 has a trivial center, so which makes things easier. If the center is non-trivial, things are complicated. And there is also an open, more theoretical point, is that what happens when you have these encoded theories and you have errors, how do they scale? Because these errors now, they are affecting the encoding strategy, so they might also become no local perturbation on the original language. So this is something which is yet to be understood in full glory. Okay, again, so these are, again, my collaborators, the people, and these are the references of these two works, and I'm done. Thank you for your attention.
Thank you, Marcello. We have time for a couple of questions.
Maybe I ask a quick one, but I see a raised hand, so.
So Alessandro can go first and then you, sorry.
Okay.
Okay, thanks. So I have a question about finite density simulations, because from what I understood, the mappings you're using here would be perfect for do like out of equilibrium dynamics. But like what type of protocols do you guys have in mind to like prepare finite density systems? Is it something like adiabatic preparation?
Oh, finite density, yes, you will have to do some sort of adiabatic state preparation. Finite density has the additional complication that you will have to tune the density carefully. In the specific implementation we have in mind, this is actually very easy for some reason, because you can do it with optical pumping, which is extremely precise. But in general, you have to think about it. It's not necessarily trivial.
I see. Thank you.
Cheers.
Zore?
Okay, so hi, Marcello. So for the SO3, how different is it from the Rishon model of SU2? So that's the quantum link model of like SU2. And now you talked about a representation that looked very similar to that Rishon representation for SU2, but I'm not sure if they are the same. Probably not.
No, they are different representation. I mean, SU2 is always in the fundamental representation, where here it is not. And also here, the fact that we are utilizing, if you want here as Rishons, we are utilizing really spin 1/2 variables. So there is no Rishon conservation at all. But this is not by chance. I mean, I think it is deeply related to the fact that when you think about the Rishon representation of quantum link, the additional U1 conservation is related to the fact that the center of SUN is non-trivial.
Right.
It is at least Z2, okay? At least Z2, or if not richer. While for SO3, the center is trivial, so there is no additional conservation law that has to somehow constrain the dynamics of the left and right component of the spin.
I see. So you're saying that if in SU2 Rishon representation, you want to build your physical states, it's not going to be just as simple as these 4 states that you mapped to Symmetry half.
Actually, they will be constrained one after the other. Yeah, it will be definitely more complicated.
Okay, thanks.
Cheers.
Excellent. If there are no pressing questions, I think it's we should thank Marcello again. And it's time for the next speaker, so Luca Asteria. Marcello, if you could stop sharing. Okay, excellent, very nice, thank you. And Luca is started.
Yes.
So, excellent, I will give you a warning in 20 minutes, okay?
Okay, thanks. Yeah, thank you for the introduction and also for the invitation to all of the organizers. And yes, so I am a PhD student in the group of Klaus Sankschog and Christoph Weitenberg here at the University of Hamburg in northern Germany. And so we also do, we do experimentally quantum simulation. And I'm going to present some of the results we recently got. And slides, I don't know. Not interact with the okay, sorry. Yes, our interest is in quantum topology, and yes, one maybe naive understanding of it, at least my understanding, so like topology is the branch of mathematics that deals with the properties that are not that are invariant under continuous deformations, like the number of walls. And so it's related to geometry by the fundamental Gauss-Bonnet theorem, where you integrate the Gaussian curvature over a closed surface, and then you get a quantized number, which is directly related to an integer, the number of walls. And the same can happen also in quantum mechanics. So if you consider as a closed surface the brilliant zone that you have in the lowest band of in the energy spectrum of a periodical system, then you have the Berry curvature, and then if you integrate the Berry curvature, you get the Chern number for a 2D system, and this Chern number must also be integer quantized. And why is that of interest? Because this topological stability provides a robustness against disorder or local disorder or noise. And so there are a lot of practical applications where this is used to produce very sensitive sensing devices, for example. And in the spirit of quantum simulation, we want to simulate these materials first with cold atoms. And so in the rest of this talk, I will then explain how we could engineer topological systems in our setup, and then present our first experiment where the geometry of the eigenstates of the lower span of a lattice was measured for the first time. Then present an example where new topological effects, the quantization of circular dichroism, were the first time measured in a cold atom setup. And then present our recent result on microscopy, and elaborate on how this could be of interest for our future topological studies. So very briefly on our setup, so we have 3 laser beams. They interfere with an angle of 120 degrees. This can produce a honeycomb lattice or a triangular lattice, or we can also, via the polarization of the laser beams, induce an offset between the A and B sublattices of the honeycomb lattice. And then we can load into this lattice fermions or bosons, potassium or rubidium, and cool them to quantum degeneracy. And so these neutral atoms then play the role of the electrons in a real solid state material. And one important tool that we have is so-called Fouquet engineering, which was already mentioned. So suppose you have an Hamiltonian which is time periodic, and which is to say after a Fouquet period t, it gets back to itself. Then you can ask yourself if you can find an Hamiltonian which is time independent, but which still describe the very same time evolution after a Fouquet period. And this Fouquet Hamiltonian is time independent. Then why would you want to do that? Because it will be once again as effective static system. That's because Fouquet Hamiltonians can have completely new properties. For example, they can break time reversal symmetry as proposed in the Haldane model. And this could be realized by moving the optical lattice periodically in a circular fashion in real space. And this creates can be used to engineer tunneling elements which are complex. And the Haldane model was proposed by Haldane like 30 years ago or so, as the first example of a system without a net magnetic field, which still possesses the features of the quantum Hall effect, because it identified correctly the main important ingredient, which is the breaking of the time reversal invariance. This was realized for the first time in Zurich with a similar setup to our own. So that brings me to the first experiment I'm going to present. How can we access geometry of a topological system? And so in our setup, instead, we start with an offset between the A and B sublattices of the hexagonal lattice. So at the beginning of the dynamic of the experiment, the bands are completely flat. We have 2 bands, and in the block sphere representation for every point momentum space, the states are pointing up, towards the B states. Then we ramp the amplitude of the Floquet driving. We increase the amplitude of in real space of the orbits of the Floquet drive, coupling the two initially flat bands to acquire this dispersion, and also changing the geometrical properties. The Berry curvature may appear or be spread over the whole brilliant zone. And one can also induce topology, a Chern number, in this way. So these Floquet eigenstates are then different, pointing not anymore upwards, but rather at some point in the Bloch sphere, which might be quasi-momentum dependent. At this point, we start our measuring procedure. We stop abruptly the Floquet drive. We project back to the flat bands with a big offset. And then at this point in the evolution of the states in the Bloch sphere is just a precession. And then at the end, we do time of flight, which is to say we measure the momentum distribution of the atoms, which have then this form. It's an interference between the two sublattices for every point in momentum space. And we can see that there is this dependence from theta. This should be theta from K, sorry. And this should be phi from K, of course. And there is dependence from the amplitude of the superposition and from the initial phase of the Floquet eigenstates, but also dependence on this evolution time in the system with the flat bands. So this means that we can repeat the experiment for different values for different hold times, and then we get the experimental picture of this momentum density distribution, which looks something like this for different times. And then we measure, for example, for these 3 points in momentum space, as a function of time, we get such oscillations, which we can then fit to this formula we got. And then from that, we get theta of K and phi of K, and then we reconstruct fully the initial state. For every point in momentum space, we know the angles, and then we have the complete state. So then we compared it with theory, and notice a very good agreement. But then if we have the full state description, then we also know everything about the geometry of the system. It's just some math to get the Berry curvature. And from the Berry curvature, we have just to integrate over the first brilliant zone to get the Chern number, which in this case is almost the same red and blue. So it's 0. And yeah, so this proves in cold atoms, you can really look at, in a very detailed way at the geometrical properties of the system. And yes, this particular technique then was used in a number of follow-up experiments, which I don't have time to talk about. Then you see all the people that were involved in these experiments. So I started joining about when the first data of this last experiment were taken. And I'm yet now going to move to another experiment with it, which was not based on this state tomography technique, but rather it's like a novel topological effect, which was for the first time demonstrated with cold atoms. So like for topology of Chern insulator, the paradigm is basically the quantum Hall effect. So you have a force, you apply force in one direction and you get a quantized response into the perpendicular direction, which is proportional to the Chern number. But then in 2017, there was this proposal in the group of Nathan Goldman in Brussels. They showed that also the circular dichroism has to be quantized by the Chern number. Circular dichroism, I mean, one has a Chern insulator, then it introduces a perturbation which can have two possible chiralities clockwise or anti-clockwise, and then one measures the difference between the two signals. By signal, I mean how many particles are transferred into higher bands. And this difference is quadratically, has a quadratic dependence on the perturbation, but it's still linear on the Chern number. And of course, they gave a very detailed proof or how is that so. And this perturbation is like the one that electrons or charged particles would see in presence of an oscillating electrical field, which has this expression. And if one can go into the frame where the symmetry of the lattice is restored, and then the perturbation would look something like this with these derivatives of the unperturbed Hamiltonian, which then if you plug into using the Fermi-Golden rule to get the excitation rates, and then you sum over all frequencies, take the difference between the two possible chiralities of the perturbation, and then you sum also over the whole barrel and so on. It's quite involved, but then you get the Chern number. This circular dichroism has also to be quantized by the Chern number. But it's also something a little bit different because it's because of the coupling calculated in this way. It's quadratic with the perturbation, but it's the very same dependence from the Chern number. How can that be? So in this proposal, there was also an elaboration on the link which between these two effects, which is provided by causality in the Kramers-Kronig relationships. Where one can say the quantum Hall effect is the reactive part of topology, and circular dichroism is dissipative counterpart, but they are really both of them one half of the plethora of phenomena that into the Chern insulator can happen. So now to how we could try to realize this. So we still start in our experiment with an offset between A and B sublattices of the hexagonal lattice. Here we see our phase diagram, which is say as a function of the Floquet drive frequency and the Floquet amplitude. So for zero amplitude, we don't drive the system. We start statically, then we start driving, and then go into about the resonance where we couple exactly, we couple resonantly the two bands, we can get topology. And then we stop at a certain point for different Floquet drive frequencies, and then add a second frequency in our Floquet drive, in our shaking, moving of the lattice in real space as a perturbation. And this is quite nice. So we have a dynamical system, a Floquet system, but we can do spectroscopy on it as long as the second frequency, which we add up, is much smaller than the first one. And we had this separation of time scale, so we could do that. And then at the end of the protocol, we have to measure how many particles we transfer to the higher bands. And so we can do band mapping. We first ramp down the Floquet drive, and then ramp down adiabatically the lattice depth to 0, such the quasi-momenta get back mapped to momenta, and then we can see most of the atoms are in the second Brillouin zone, which because of which corresponds to the first Floquet to the lowest Floquet band because of this Landau-Zener sweep. But then also we can see that because of this spectroscopy, we get some particles also in the excited Floquet bands. So we measure this ratio for different for two different cases. One where we expect Chern number 1, one where we expect Chern number 0, for different frequencies of the perturbation and for different chiralities of the perturbation. And we see that there is, since our system is always chiral in the first place, a chiral perturbation is always, I mean, the reaction of the system is dependent on the chirality of the perturbation. Therefore, In this case, the two curves don't align perfectly, and we don't even expect to, but their net contribution, their difference, this gray area integrates to a value compatible with 0, whether in the chair number 1 case, this value is compatible with 1, demonstrating the initial proposal, which we wanted to. And just for completeness, I will show you the whole phase diagram as a function of the Fouquet drive, comparison with the ideal theory, and then with a theory which includes some, but not all, of the experimental imperfections to demonstrate why it was not so smooth and as in the one would expect for the exact quantization of the chair number. And so we could demonstrate for the first time this new topological effect, but also we think it would be of high interest because there is this proposal where it is shown that it should work also with fractional quantum mole states. Yes, so now for the last part of my talk. This part is not so much topological, it's just our recent work on microscopy of cold atoms setups. So of course, this whole description of topology works in momentum space because Berry curvature lives in momentum space, and then the chair number is the integral in the orbiter and so on. But then when we put one topological insulator next to a normal insulator, then the spectrum can look something like this, with a linear, with a dispersion, with a positive group velocity, which lives in the band gap, and these states corresponds to live also are localized on the physical edge and the interface between the two phases, and they are basically the semi-classical skipping orbits of the quantum Hall states, if you want. So of course, there will be much of interest to go into this real space description and ability to look at the system. But in cold atoms, there are a lot of possibilities of doing that already. Like for example, the quantum gas microscopes, where they have single site resolution and single atom resolution, which allow them also to measure the full quantum correlations. But these systems are mainly limited to these systems and also to a very low occupation number. I would say not bigger than 2 also typically. And yeah, as we just mentioned, there are other microscopic techniques which may be based on ions or linear phenomena, but all of them have some feature and limitations. And we recently proposed an alternative method, which is somehow different, but somehow also combines many of the nice features that this already existing system have. We call it the quantum gas magnifier. So, and our idea was that high resolution imaging is the effort to get closer and closer to the quantum system. But what we instead proposed was to bring the quantum system closer to us. So instead, we chose to use a matter wave lens to magnify the density, the real space density distribution of the atoms, in order to be able to image this distribution with a single shot image. So how does it work? Like suppose we do some physics, like we used bosons in a triangular lattice with a weak confinement in the perpendicular direction, as called lattice of tubes. And then after that, we start the measurement per protocol. We quench an harmonic potential, we switch off the lattice and quench to an harmonic potential. And then the atoms get a momentum which is proportional to the initial position. And then we do standard time of flight. And then we measure this momentum, which was the initial position. So we measure the initial position, with a magnification which is given by the trap frequency and the time of flight. And for our typical parameters, this can be as high as 90, this magnification. And so we are able then to use standard absorption imaging to get such a picture, for example, of our lattice. And yes, because of course we are not anymore limited by diffraction or other optical effects, because the lattice spacing is now gone from like 700 nanometers to 60 micrometers. This, of course, no problem anymore. We can, yes, and for example, in this image, there might be like 700 atoms in the central tube, in the central tube, sorry. Yes, so we wanted to characterize the resolution we got. And we did this experiment. Like we have this hexagonal lattice, once again with the offset, we crunch the potential to a situation where to a dimerized lattice where the A and B sides are much closer along one direction. And so you can see at the beginning, all the atoms are sitting in the lowest side, and then there is some dynamic and they can tunnel out. And yeah, more, the whole time evolution is seen in this cat. We plot here the density distribution along the cat, this cat. So you can see at the beginning, we have just one peak corresponding to the left side. After 90 microseconds, we have 2 peaks corresponding to the sublattices. And in general, one can recognize this oscillation dynamics and this tunneling dynamics. And we compare the experiment with a simulation with this about a resolution of about 80 nanometers in the lattice, not in the magnified lattice, which is quite nice. You have to compare it with the lattice spacing, which is 700 nanometers, demonstrating that we can, with a single image, like this, for example, observe the dynamics at this level. And this, yes, we find it very interesting for topology because many topological models involve higher bands. And these dynamics can be described just by the S bands, S orbitals of the two sides, and the P orbitals of this same two sides. Yes, so I don't have much time left, so I can.
1 or 2 minutes left. Yeah.
Yes, we do. That we do. Yes, we also, another thing that we tried was to use the magnetic trap where the atoms are confined in the along with the lattice, and to use these position dependent resonances to a state which has losses which get lost from the lattice to shape the density distribution. So we could, for example, like shifting the atoms to the slope of the magnetic trap. Yes, basically produce almost arbitrary patterns using these symmetries. And for example, create highly excited states. As an example, we studied the thermalization dynamics after we cut out half of the atoms from the system. And the connection to topology this time, we hope that it will be a nice tool to prepare wave packets with at the interface between two different topological regions to study wirklich this edge physics. Yes, and that brings me to the summary. So I presented our first experiment where with cold atoms, the Berry curvature and the full geometry and state tomography of the topological system was possible. Then I presented a novel topological phenomenon, the quantization of circular dichroism, and then gave a brief overview of our recent progress on microscopy of cold atoms. And I mentioned that there were the names of the people in the tomography experiments. So I was involved in the last 2 experiments I presented. So I would like to thank the persons I work with and you all for your attention.
Excellent. Thank you, Luca. Any questions? We have a few minutes. So maybe I can ask a question. In the integer quantization of the Chern number that you showed, it wasn't quite 0, right? It was like 2 sigma.
Yes, this one you mean.
So there was
in the first one, the very first one.
Yeah, the first one. Yeah, earlier.
Yes, I guess this is like I cannot be completely sure because I wasn't part of this experiment, but I think this is just a statistical error which comes from the fits that you get in order to measure the angles of the Bloch sphere for every point in momentum space. And probably this is just the propagated statistical error, but then there is still something systematical or so.
Which we can roughly see the magnitude of, right? Yeah.
Yes.
Yes. Okay, great, thank you. Any other questions for Luca?
I'll have a quick one.
Yes.
If nobody else asks, I can wait.
Please,
Yeah,
please.
go on, please.
Can I go ahead then? Luca, I have a question. So in the measurement, I mean, effectively, right? The circular dichroism that you have is just directly proportional to the current response, right?
Sorry?
The circular dichroism that you're measuring is directly proportional to the current correlator, which is this thing here, which is the the Chern number.
Mm-hmm.
So I mean this is something that I think people knew already for a long time. So the message is that you were able to make that measurement, right, in the particular structure that you have.
I mean, this was like a heating measurement, if you want. Like we heated the sample with 2 chiralities and then looked at the difference of the heating signals and then found that this was quantized with this was not a current measurement. It was like you look at
no, I understand, but formally this thing is directly proportional to the current correlator, right? So this has been known for a long time. So the question that I have for you, if you're heating that up, what are the effects of temperature that you have on this quantization?
Yes, I mean,
if you were at strictly at 0 temperature, right? We know that that response is proportional to the current correlator. That's strictly 0 temperature.
Yes, I mean, you have to pay attention with what you mean by heating up, because there is one heating that is present in this phenomenon, which is this resonant transfer to higher bands, and the heating that you say, okay, I don't start with T equals 0 at the beginning. So the first heating is the one that you want to measure. The second one, it may change your signal. For example, we of course in the experiment don't have T equals 0. So this also might be a reason why the signal is not perfectly quantized. So if you start with some, for example, it's for a fraction of atoms in the second band has Chern number equals -1. So this would a little bit decrease the signal. Was that helpful?
Yeah. So in effect, I mean, in some sense, you're saying that you're measuring some average of the Chern numbers, whatever, of the current response at a given temperature, right? So if you could, in principle, lower and lower the temperature further down, then then the agreement would be much better.
Yeah, this
You
might
don't have
be
this
the case,
broadening.
but
This broadening
yes,
is a thermal broadening, right?
yes, might be due to the fact that temperature is not perfectly zero, but then there might be some other effects, like for example, we don't have an infinite system, and there are all phase transition are not smooth anymore. Yeah, so also we still have some harmonic confinement during the experiment because of the very same lattice beams which make the optical lattice. So it's yes, just typical experimental imperfections.
Okay, thank you.
Excellent. Okay, thanks again, Luca. If you could stop sharing your screen, and now Zore Davudi has the floor. And Zore, you have 25 minutes.
All right, let me share my screen. Full screen. Does it look good? Do you see my cursor?
Yes, yes.
All right, perfect. All right, thanks very much for this great workshop that you put together and for inviting us. It's a pleasure to be speaking here today. So I looked at the topic of the workshop. I was having kind of a hard time deciding what topic to talk about. I could have talked about nuclear physics calculations within the framework of Lattice QCD, some of the interesting progress that has happened in the few body sector on that front. But I also had the option of talking about some of the recent progress in ideas for quantum simulation of nuclear physics and lattice gauge theory models. And I looked at the session I was in. I was the last to send the title, and I looked at the title of Marcello and Luca talk and kind of figured that implicitly the organizers want me to also contribute to the topic of quantum simulation. So kind of I took that hint, and as a result, this is what I'm going to talk about. I'll tell you about some of the ideas on how to take advantage of trapped ion quantum simulators to eventually, hopefully, simulate models of interest in nuclear physics and lattice QCD. All right. So to put things in the context, of course, we all know that quantum simulation is about leveraging a quantum system that can be controlled with another quantum system that is more kind of experimentally or computationally accessible compared to the models that we are dealing with that are kind of elusive in that front. So in the context of nuclear physics, we're hoping to start simulating from first principles nuclear physics phenomena from quark and gluon degrees of freedom of a standard model, build a nucleon, build a nucleus out of those nucleons. But we of course know that these are what are sort of forming more macroscopic objects out there, such as the atoms, and then materials, molecules, materials, and eventually these macroscopic astrophysical systems that we're interested in really making predictions for. And what quantum simulation means is to kind of leverage these systems that are kind of fundamentally and drastically different in terms of their degrees of freedom or the scales involved and interactions and so on from the systems that we're interested in studying, and do this through either kind of a digital approach or kind of more natural and analog approach. So that's kind of what the general picture of what this program is all about. And of course, for someone in this community who's interested in studying a strong interaction physics, the ultimate goal is to use a controlled quantum system, such as these trapped ion simulators or other systems that we heard about today, such as cold atom systems and Rydberg atoms and so on, to eventually study physics of QCD. Of course, this is going to be a long road. We have to identify smaller steps on how we take these simulators and hopefully make them more advanced and kind of map them and match them to the simulations that are of higher and higher complexity as we move along in this program. Also, Marcello mentioned that there are different approaches to the quantum simulation. two of the most familiar approaches are analog simulations and then digital simulations. In an analog simulation, you find a system that has the closest properties to the system of interest, that your target system that you want to simulate, or has a degree of control such that you can engineer Hamiltonian of that system such that it mimics the Hamiltonian of the target system. And if you can do that, if you can map the degrees of freedom as well as the Hamiltonian naturally to the simulator that you have in hand, then the time evolution or dynamics is very natural. You just let the system evolve. You just run the experiment, right? In a digital approach, which is more universal and flexible, so it doesn't require matching really sort of the intrinsic properties of your hardware to your target system. But in turn, it requires sort of breaking up the time evolution operator one way or another. So the most familiar one is to this Trotter-Suzuki expansion of time evolution operator, or this kind of product formulas. But there are other approaches, but they are kind of behind all these approaches is the fact that you break down the time evolution operator to its steps. They can be mapped into universal single and two-body operations, so that you're kind of agnostic to the underlying hardware. You have to just figure out what algorithm you require to simulate this time evolution operator given this universal set of gates. And of course, there are analog and digital hybrid approaches that I would also talk about that kind of combine the two ideas here. You still have the digitized time evolution, for example, but you take advantage of more flexibility in mapping the degrees of freedom, as well as more sort of extended set of gates and operations that you can imagine given the physics of the simulator. So let me focus on this chapter on quantum simulator, give you a very quick tour of the underlying physics. So for the sake of this talk, I'm interested in one-dimensional Paul traps. So this is a radio frequency Paul trap. It's more confining along two of the direction compared to this axial direction. And as a result, you can sort of arrange these ions in a one-dimensional line. And as you can see, this is a picture of real ions in experiments. They can be arranged to be spaced by a few micrometers in experiment. And then you address these with a set of lasers, and you are able to engineer interesting Hamiltonians. What can you do? Let's think about what the Hamiltonian is for these systems. So the free Hamiltonian, without introducing any lasers, has, of course, two parts. You can imagine that the two of the stable lowest lying internal levels of these ions can mimic a qubit state for you. So this is a two-state system up and down. And the frequency difference is quite high, of the order of gigahertz in various different ions. So this is one of the highest scales or frequency scales in the problem. And then therefore you can have sort of these operations with these sigma Pauli matrices on the space of these two-state qubit. There's also another term to the free Hamiltonian, which describes the fact that these ions are sitting in a chain. They have Coulomb interactions all to all, but they also see a common confining potential. So in principle, you can solve this quantum mechanical problem and come up with the normal modes of motion that are described in terms of these phonon modes. So these A dagger A operators are creation annihilation operators for the normal or local modes of motion if you're in a certain regime of parameters. And these are the frequencies that are identifying sort of the spectrum of these phonons. Again, this is one of the highest frequency scales in the problem, but not as high as, of course, this qubit frequency. This is of the order of megahertz in actual experiments. Now, the interesting part, when you introduce a laser, you can have these electric dipole interactions. So you just decompose these interactions in terms of the parameters of these electric fields of the lasers, including kind of the intensity of the laser encoded in this Rabi frequency, the beat note frequency of these pairs of Raman beams, which is the way to do it in certain experiment, the difference in the phase of these Raman pairs, in their momentum vector. And these are the parameters that depend on kind of the lasers that you introduce, and you have control over them. So these are sort of the flexible parameters that you can optimize to get certain type of interactions. The two parameters in this color orange are the ones that are depending on the trap itself. For example, how confining you can make your trap, right? So therefore, the position of the ions would be affected, this frequency or the spectrum of the phonons would be impacted. And of course, there's also this sigma operations that are operating on the state of the qubit. And as already you see in this term, you can have correlated or entangled spin phonon operations as a result of this interaction term, okay? So let's look at this more carefully by going to the interaction picture, because as I said, there are certain scales in the problem that are just large. So things would oscillate very fast with these frequencies, and over time they average out to zero. So you can kind of get focused on more slower kind of dynamics in the system. And that's what is kind of the basis of this interaction basis Hamiltonian. So what are the terms now? It's just sort of a rewriting of the previous interacting Hamiltonian, using this free Hamiltonian to go to the interaction picture. Again, you still have these operations on the state of the qubit with these Pauli operations. Now you have this factor. This is now written in terms of creation and annihilation operators of the phonons. And this is just coming from expanding e to the ik dot x operator in terms of the usual expansion of the x operator in terms of creation and annihilation operators of these normal modes of the motion. And the last term is everything that is left, all the frequencies and phases and Rabi frequency and so on, which again is something that you have control over in experiment. You can change all these parameters depending what kind of lasers you set, okay? So now it looks kind of complicated, right? Because you have this complicated exponential operator of the phonons, and we have to deal with it somehow. So it's good to go to a certain regime, which is possible, and that we can expand these operations order by order. For example, you can have something called a carrier transition at order eta to the 0, which is this lambda key parameter, very accessible in experiments. And what that means is that there is no phonon operation. Everything is pure spin operation. So you can have pure kind of a spin, a coherent spin transitions between the two states of these qubits. And this is really the basis of one qubit operations in these trapped ion quantum simulators or computers. Interesting things happen at order eta, because now you can start to couple a spin and the phonon operations. And in particular, you can have something called red sideband Hamiltonian, which induces these transitions where the spin of the qubit is changed. And in the process, you can sort of absorb a photon. Or you can emit a photon in what is called a blue sideband transition, okay, which would be the other order eta to the 1 contribution to this process. And you can go higher and higher, but higher order terms are going to be suppressed if you remain in the regime where this eta parameter is small, which again is very accessible. But this is just the single qubit operations as well as spin phonon operations. For the purpose of quantum computation, we're also interested in the spin-to-spin operations, right? So that would be 2 qubit entangling gates, for example, in a quantum computer. How is this achieved is through a well-known process called adiabatic elimination technique. And what it is at the heart of it is to use these phonon degrees of freedom to virtually sort of mediate interactions between the two spins. So they're kind of in the context of nuclear physics, they're pions of nuclear physics. You have nuclear-nuclear interactions that are kind of transmitted by these pions, in this case by phonons between the 2 qubits. And what it works is that you have the combination of red and blue sideband transitions. And in certain regime for the intensity of these lasers, as well as the detuning to this sort of sideband transitions, you can achieve the complete elimination of the occupations of these intermediate states and effectively, for example, couple up, and down a state of the qubit. And that certain regime is where delta is much larger than this Rabi frequency times eta, which is what I call G. Okay, so this is sort of really the basis of it. And you might hear the Molmer-Sorenson scheme or Sirac and Zoller scheme. They are kind of based on this kind of idea. And so for the sake of time, let me just not go over this. This is just some slide about how this actually is derived to certain limit. But I just want to say that really effectively, the Hamiltonian is now a spin-spin type Hamiltonian, which is kind of an Ising model type Hamiltonian. All right. So what are the certain modes of these trapped ion simulators? Well, in the digital sense, we can have, again, a single spin gates that I talked about, these carrier transitions. You could also have the two spin gates or these Molmer-Sorenson transitions. I just told you about these, right? So these are really on the digital side, the universal set of gates that you can build in principle any unitary from. In an analog set, there is no gates, as I talked about. But then the certain type of Hamiltonians that you can build are either kind of this Ising type Hamiltonian with an effective magnetic field, XX type Hamiltonian, which are kind of long range power law type interactions, which are very interesting, having the basis of a lot of interesting experiments on spin physics and seeing all sorts of interesting dynamical and non-equilibrium physics in these systems. What you can do is to design also certain type of parameters in this experiment with a certain type of lasers to actually achieve a Heisenberg type Hamiltonian. So this is a little bit more complex, and that would be useful in the context of, for example, certain lattice gauge theories, where you can have XX, YY, ZZ operations at the same time in an analog way with an effective magnetic field, okay? We have also extended this to 3 spin interactions along with 2 and single spin interactions, where again, it could be useful in the context of a lot of interesting spin physics in the condensed matter, but also certain lattice gauge theory models. So that would be useful. But what about the analog digital approach? Well, in this approach, then you have single spin gates and the Molmer-Sorenson gates as before. But remember, I told you there are also spin phonon type transitions. Why not taking advantage of those to act like a gate, right? So we don't have to limit ourselves to just 2 sets of gates. We can have a spin phonon and phonon type gates as well, designed to simulate the theories more efficiently compared to either digital or analog setup. And I told you examples of this in a moment. So lattice gauge theory example. So I'm going to just focus on one simple example, go through all these modes of operations and convince you that each of them has their own benefits, but also disadvantage. And we're in the near term implementations of these models, we have to figure out what's the best route to get to the answer quickly. So this is the lattice Schwinger model. If you're not familiar with this, this is 1-dimensional, 1 plus 1-dimensional quantum electrodynamics coupled to, in this case, a staggered matter. So there is an electric field term, there is a gauge matter coupling sitting here, and there is a staggered mass term, okay? So this theory has very interesting physics, and in particular is a prototype for QCD, it turned out. You can also simplify this model because it's a 1-dimensional theory with open boundary conditions, and you can actually effectively end up with a spin physics, right? A spin Hamiltonian. And in a sense, you have nearest neighbor spin-to-spin interactions, long range spin-to-spin interaction with the sigma Z type operators, also effective magnetic field. So really the spin representation of Schwinger model is nothing but the Heisenberg model, okay? Which we know how to do in an analog fashion now in an analog trapped ion simulator. All right, so let me go through the different modes of the simulation for this particular lattice gauge theory model. So let's say that we are interested in digital operation, but for just this spin representation that I gave before, where there is no gauge link, which means that we've already taken care of it. We're using the gauge symmetry and in the problem in Gauss's law, so that we can just map the fermions to the spins through just Jordan-Wigner transformation, for example, which is what is done in this Hamiltonian. So that means that we don't have to encode these gauge bosons, which is nice. But also then in a digital sense, the circuit is quite simple now. We have Mollmer-Sorensen type gates for this first part of the Hamiltonian. And then you can have all-to-all sigma z type interactions, which is just the Mollmer-Sorensen gates up to unitary transformation on the qubits. And this is sort of the circuit for each trotter step. This is really the basis of kind of what was done in the first experiment by the Innsbruck group. I think Marcello was part of that, and kind of mentioned this progress on the digital side. And it was quite exciting. This is a real-time dynamic of the Schwinger model within this spin representation of the model. And kind of we're extending the same thing here in the trapped ion simulator in Maryland for larger systems and larger simulation times. But what about the analog approach? Well, again, this spin representation of the Schwinger model is nothing but the Heisenberg model, as I told you about, right? And we have figured out how to encode the Heisenberg model with 3 sets of Raman beams in experiment. Requires a classical optimization of the parameter, but that classical optimization turned out to be easy and scaling just linearly with the number of ions. And this is the result of that parameterization for Rabi frequencies and the detuning of these ions, these lasers, such that, for example, you have this XX Hamiltonian, which is completely nearest neighbor, like perfectly, which is nice. You can also have these ZZ type interactions in the Heisenberg model, which in this case of the Coulomb interactions in 1D has this particular all-to-all, but kind of falling pattern. You can also achieve that perfectly. So what about the digital approach when you don't remove the gauge links, which would be this Hamiltonian that I showed you in the top of the page when I introduced the Hamiltonian? But what that means is that you have to take the gauge links or this electric field basis states and kind of encode them into the qubits. And just the naive encoding of this would tell you that you have of the order of the logarithm of the cutoff on the excitations of the electric fields, number of qubits to add to encode. So you can already see that the requirements for encoding the full gauge matter theories is going to be very high because of this. But not only that, the circuits and implementations are going to be more complicated because not only you have to couple now all these qubits to these nearby fermions, but also these qubits among themselves because you have an electric field, a square term sitting here. And this is kind of a nice circuit. It was written down by Shaw and collaborators last year of how to actually do this time evolution within this model, given all these complicated mappings and correlations among the different qubits. And you can already see that it's this complicated circuit. You don't have to know exactly what's going on, but there are lots of kind of Mollmer-Sorensen type gates or CNOT gates and so on. And they actually counted the near-term cost of operation for certain target accuracy for certain coupling regime. And it's of the order of hundreds of thousands of entangling gates to reach the accuracies that we're interested to gain something interesting in the continuum limit. So these are the type of studies that we really need in the quantum simulation era for all sorts of gauge theories to figure out what it takes to actually eventually do lattice QCD with these quantum systems. And finally, I want to tell you about this analog digital approach, because now here we can say, all right, in near term, we don't have to kind of limit ourselves to just qubits. We can take these gauge links and then map them to these phononic degrees of freedom, which are the bosons in the system. So if you have a boson in your simulator, why not take advantage of it, provided that you can have control over these bosonic degrees of freedom as well, just like with the qubits. So you can do that. And in fact, you can see some of the details here. We were inspired, in fact, by these discussions in the context of condensed matter theory, sort of these coupled electron phonon systems that are interesting to study. And there were some ideas there. And we thought that we can also implement them for gauge theories and scalar field theories and so on. And the circuit representation is now much simpler because we have this spin phonon gates and phonon gates that will kind of simplify the circuit that I showed you just in terms of the qubit degrees of freedom. And you can kind of count the amount that you gain. It's not exponential, of course, but it's upon a polynomial substantial polynomial cost reduction that you should keep in mind in near-term applications. The question is that, is it really true that the phonons can be controlled experimentally and there are going to be new degrees of freedom that we can work with? It seems like it is, at least for small systems. This is an experiment in Monroe-Linke group a couple of years ago, when in a 3-ion system, they look at things like the phonon couplings and hoppings and blockade, and they were able to actually sort of detect these things with high fidelity. So that's quite inspiring, and maybe we have to also think about whether these systems can be used for lattice gauge theory simulations in the future. I have more examples, I think, but I think I'm at the end of my time. I probably only have 1 minute at this point, looking at my watch. So I just mentioned that we have looked at other gauge theories in higher dimensions. You can sort of play the same game. You don't have to limit yourself to just one-dimensional theories, because you have a lot of control in the experiment now, and you can play the same optimization game to get the coupling patterns that you have in certain gauge theories in 2+1 dimensions. These are 2 examples that I have in these slides. I'm not going to go over them. Also, this analog digital approach, we applied it also to scalar field theories coupled to fermions, which is a Yukawa theory. And there are some interesting features there. This is kind of the mapping of the model Hamiltonians. This is the circuit and the cost reduction that you gain as a result of doing this hybrid approach. If you're interested, just check out the paper that we had. So in the last couple of seconds, I just summarize. I told you trapped ion simulators have become a successful platform for quantum simulation of many-body physics. The first successful implementations of gauge theory models on trapped ion simulators and computers have emerged for small systems. Hopefully I convince you that we can think about more extended degrees of freedom in this system. In particular, phonons can be manipulated and measured in these systems, hence the possibility of using them as both virtual and dynamical degrees of freedom in experiment. Simulating complex dynamics of quantum field theories may benefit from digital, analog, and hybrid implementation, depending on the problem at hand. So that's important. And I think as an outlook, I think as these systems scale and improve, we must come up with resource-efficient algorithms that are tailored to our problems, and paying attention to this hardware architecture is important. In particular, I think co-development and close collaborations between theory and experiment would be very crucial, I think, in the upcoming years in this program. And the theoretical development has also to sort of come a long way to kind of take advantage of what's at the moment in the market. We have to have efficient Hamiltonian formulations, how to impose gauge symmetries, as Marcello was telling us about, becoming clever about the encodings and respecting the symmetries at the same time. And I want to also mention that in the same way, effective field theories of nuclear physics can also benefit from some of these ideas, because there's very, very much similarities between the formulations of the effective field theories as well as these matter gauge theory type interactions. And as a last word, I want to say that I think the Condensed Matter community has been ahead of us for at least a decade or so, or maybe more, in terms of leveraging quantum technologies, but also kind of learning and understanding condensed matter system better in the context of quantum information science. And I think in the high energy nuclear physics, this is really something that has started now, and our community is really paying attention and getting excited by this idea. So I'm guessing hopefully in a few years, we would be able to catch up with our friends in the condensed matter community on that front. And these are my collaborators on various different projects I talked about, and my apologies to a lot of people that have done really good, exciting work along these lines as well. Thank you very much.
Excellent. Thank you so much, Zoe. We have time for a few questions. Marcello, please.
Okay, I was clapping, but I also had a question, so I take them.
Thanks, Marcello.
So there I have, I mean, you flash over this idea of Chern-Simons, and maybe can you give us a somehow intuitive idea? Because when I think about Chern-Simons, typically I think it's something that if I put it on the lattice is complicated business, yeah, because it's true, it's pure topology. So what are the tricks that you utilize to make it somehow endable somehow? Let
me show this slide again. Yeah, so this is a very particular Chern-Simons theory, right? So as you can see, it's not sort of a pure gauge. I think it would be challenging to do the pure gauge Chern-Simons theory as I was thinking about it at the time. This particular model is kind of coupled to these fermionic terms. Okay, so this is the type of Chern-Simons that we are looking at. So there is the A dagger A field, but then there is this A mu F mu nu type term sitting here with this epsilon. And it turned out that, and I can tell you about the details of this later on, maybe, you can map this Chern-Simons theory of this particular type to a Heisenberg model in 2+1 dimension with just spin 1/2. So there's an interesting kind of duality that is between these two models that you can work out. In particular, I think you can use the advantage of the gauge fixing and Gauss's law, and you kind of end up with this dual mapping. So this is a very particular case. Okay. If you would have asked me to do a pure gauge theory with the Chern-Simons theorem, I think that would be more challenging. I don't know how to do it within this framework, but that's kind of the trick.
Thank you.
No problem.
I have almost a question. It's not clear it's a question, but I'm going to pose it anyway. So early on, you talked about the interaction picture, talking about the Hamiltonian, right? So when I hear in quantum field theory, when I hear about the interaction picture, I think of perturbative expansion. And you did, show order by order. But of course, we don't have to do quantum field theory, in a perturbative expansion, right? So at the level of the Hamiltonian, is there such a way of handling that Hamiltonian without using, like that time dependence, whatever it was, without going to the interaction picture?
Yeah, of course. I mean, the point is that, as I said, there is a separation of the scales in this problem. So you can say, all right, let me start from the full Hamiltonian and then just simulate the full dynamics. What you end up with is that if, for example, if you want to sort of classically describe this Hamiltonian evolution, you have to have very, very small time resolutions to resolve oscillations that are as fast as these gigahertz of oscillations, as opposed to things that are of the order of, for example, kilohertz, right? We're interested in these detunings and Rabi frequencies that are of order of hundreds of kilohertz to maybe megahertz. So it's kind of an effective theory, in my view, this kind of interaction picture Hamiltonian, because we're saying, all right, in this Hamiltonian now, we make it, it's kind of sitting in between Heisenberg picture and Schrödinger picture, right? Something in between where we kind of deal with those fast oscillations. And it's kind of a change of frame in a sense, right? We're sitting in a frame that is kind of oscillating very fast so that we can focus on the slow kind of oscillations, the effective dynamics that we're interested in, and we're going to see it at the time scales of the experiment, which are milliseconds or higher, right? So it's kind of an effective picture in a sense.
Okay, excellent. There's a question. I think Srimoyi has a question.
Hi, Zoe.
Hi. Oh, hi. How are you?
I'm fine. How are you?
Good.
Yeah, so I had a question about the question before this. So we were talking about Chern-Simons theories coupled to fermions, right? And you were saying that this is a very particular example which can be mapped to the Heisenberg model.
That's right.
But I was wondering, if I go to very low energies, if these are massive fermions, then, the low energy EFT is just, a pure Chern-Simons theory, right? So I was just wondering whether, what you did really implies that you can map any Chern-Simons theory to the Heisenberg model, or is there something?
At low energies? I think the sort of what I realized from literature is that there is still some ambiguity in how to define Chern-Simons theory on a lattice, just because it's kind of topological and you're kind of breaking that by introducing certain geometry, and there are various ways to discretize and still keep the geometry or topology intact at low energies. but you're probably right. I think at low energies, this would be still a good description of the pure Chern-Simon theory. But I don't know how much of those complications with sort of breaking the topology would still apply. Probably less so in the low energy side, but.
I see. Okay. That's interesting. All right. Thanks.
Thank you.
It had to happen at least once today. No, I was muted. Yeah. So thank you once again, Zore, and I would like to thank the speakers for all the both sessions today. Now we are changing gears slightly, so we have 30 minutes budgeted for the open discussion session, and the way we've planned to do this is each day we've asked one participant to kind of start leading the discussion, which means offer some thoughts about either the talks of the day or the field or the fields, because this is an interdisciplinary workshop. So today Dorte Blume was kind enough to take this role. So I will stop speaking now and Dorte may start.
Yeah, thank you, Alex. Thank you to the organizers for putting this together. And also thanks to all the speakers this morning. So I think we started off this morning with nice talks about the dynamics and transport properties in real time. And then the second talk also sort of connected to this quite nicely, thinking about structure and the response. And we had sort of a comment that maybe once we get quantum computers to work, we can do a lot more and really look at the real-time dynamics. Then we had a talk that, and actually sort of two talks that touched quite a bit on multi-band physics. And I think there an interesting question is if this multi-band physics from condensed matter and cold atom systems, if that transfers over in some sense to nuclear systems and possibly high energy systems. And then, I'm just giving sort of a very brief summary. We had talks on quantum simulations, which on the one hand sort of looked at simulating effective field theories in some way in real time, so to speak, but also using the same techniques to sort of build toward a quantum computer. And so I think that's sort of a very brief, rough summary of what we heard about today. And so I think it'll be good to hear from participants what possible connections are. And I think I might ask Joe to start with. Joe, you said that you would like to see more cold atom data. So I'm assuming these were cold atom data from experiment, sort of related to the dynamics, possibly going beyond linear response. Do you want to say a little bit more what's on your wish list, Joe, and why?
Well, this is somewhat uninformed because it always depends on what's experimentally possible to a great deal. So I would like to see, if possible, more information on various kinds of responses, just to see how much theoretically we can understand these responses. And that, that can range from the momentum dependence, if we insert different amounts of momentum in the system, different energy resolutions, and different probes. So all those things are kind of important in nuclear physics. So if we could get, response functions at different momenta and over different energy regimes, that would be very helpful for constraining our many-body theories, I think.
Yeah, thank you. And we had one talk by Luca that discussed at the end sort of new imaging techniques, I mean, in a slightly different context. So I wonder if some of the techniques you talked about, Luca, could go in that direction.
Yes, but we demonstrate them with the lattice, just like a typical structure that one can get into a not ultra cold atom setup. Yes,
Yeah, but do the techniques that you described, do they really rely on having a lattice, or could you also use them in free space?
No, just the object we chose to image, just because it has structure, and we could verify it that it actually works. And yes, but the method should be general. Yes. I would say it might be limited by other effects like interaction. Also, they might be switched off for particular atomic species using Feshbach resonances. But then the point of the imaging technique might be what's the scale of the feature that you want to image. And I don't know if in these particular models which Joe was talking about, if the resolution is the problem.
Because you're at the sublattice side, but that's still in a free gas, it would be many spacings between atoms, right?
I mean, it's a fraction of the spacing between different lattice sides. Yes.
Joe, do you want to comment more? I take it no.
You may have heard this line, silence is argument carried out by other means.
Yeah, so yeah, I forgot to say that, of course, everybody is invited to jump in and comment. I think we have about 21.
I have a comment, maybe a comment, a request. So
please.
Yeah, I think this is very good timing to have a workshop on the kind of intersection of condensed matter and nuclear physics. I wanted to mention that a few weeks ago, we had a workshop on quantum simulation of gauge theories, and we had a very exciting session. It was a discussion session that was led by Marcello and also Alexei Gorshkov, who told us about what impact quantum simulation and quantum thinking has had on condensed matter physics, and what are the lessons that we can learn from this progress to bring to the high energy physics and nuclear physics communities. I thought it's kind of very relevant also to the theme of this workshop. So I wanted to request that Marcello, maybe you want to summarize those thoughts also for this audience. Sorry for putting you in this spot, but I thought it was very valuable set of comments that you made.
Yeah, no, I mean, I think I can summarize a part of it. I think might also be covered by tomorrow's talks, because Francesca, for instance, will talk about very similar things. No, I think there are there are several things that one can transfer from this previous condensed matter AMO / quantum information communities interaction that can be transferred to the nuclear physics and high energy physics AMO interactions. I mean, maybe one thing that should be emphasized is that there is a part of this connection that we're already there, like this unitary Fermi gas business. I think it's historically is a strong AMO nuclear physics connection. So maybe I comment more on the slightly different route, which is going towards a bit more gauge theories. I think one element is, of course, that one can learn is not only to move one direction. I mean, this is not try to transfer problems and then hope that some days a quantum simulator or a quantum computer solves them. Okay. I think that we should study how this can happen. Of course, that's very important. What Zora was doing, and I was doing, and other people. But I think it's also important to try to transfer the concepts from nuclear physics and try to understand what these experiments are doing. And at the same time, one can do that by adding elements. And one element that we have not been discussing today, but I think is very important, is the role of entanglement. I mean, nuclear physics is very rich, and I think in terms of phenomenology, and I think it would be nice to see whether we can learn something by studying some of these phenomena through the lenses of entanglement, which are typically different from the ones that rely on few body correlations, that are also the ones that I was more traditionally educated with. I think opening the toolbox of quantum correlation and entanglement is something that I would say is maybe the most important lesson here that one can decline.
So Marshall, what would be an example, a prominent example of when entanglement kind of opened the eyes in a particular condensed matter problem?
Okay, I think there were two examples. I mean, first is the development of tensor network methods. People at the beginning did not really understand when they were working and when not. And once they were reformulated in terms of entanglement, and people started understanding that these tensor network methods are good to describe certain classes of entangled states, this then opened a Pandora's box, because then people started understanding like the effect of entanglement characterizing topological order that was so far not really understood. You cannot use Ginsburg-Landau. Then with entanglement, you can characterize it. People start developing novel algorithms that instead of focusing only on one-dimensional system, they are nowadays almost standard tools in 2D. So I think that was one example of very strong impact that happened in that direction, I would say. And I think that there are a lot of interesting phenomena in nuclear physics that could be seen. I mean, there is a bit of work, I have to say, nowadays in this direction, but I know very little. And I will be looking forward to developments in this direction, of course.
Yeah, there's been some very interesting results coming out of Seattle group. I think also in Brookhaven, maybe other groups that I'm not yet familiar with. But yeah, that's true. I think this line of investigation has started, and it's very interesting, right? Can we understand chiral symmetry breaking better? Can we understand nuclear interactions and various features of nuclear interactions, and the fact that these systems are near unitarity, right? Is there anything in connection to entanglement measures that would help us to characterize or understand better these phenomena?
Yeah, my experience is whenever there are strong interactions, entanglement is typically very informative. But of course, one has to see. So.
Can I invite anyone who has any comments or perspectives on this topic? I think we would be happy to hear.
Maybe
I was.
So sorry.
No, go ahead, Alex.
Maybe I can ask Marcello to elaborate. So you said before, the traditional approach is few body correlations. More modern is entanglement. So, like in a toy, I think Zore also was hinting at this. In a toy problem, like textbook problem, like few body correlations, I guess means some operator acting on some like a Slater determinant, say, right? And yes. Entanglement in this case would be something beyond the Slater determinant, or like, could you give an example?
Yeah, I mean, the typical example, if you consider zero temperature states, which are pure states. And then we do know that if we want to access the entanglement of one region with respect to the rest, so how the two are correlated, there is a quantity which is the von Neumann entropy at the very end of the day, that this quantifies how much entanglement is shared between these two regions. And it is known that this quantity, both in quantum field theory and in many body, it is important. Then, of course, very likely in nuclear physics, you will not be happy with that. you will be happy to study entanglement within components, okay? Or scattering. These are more complicated objects, and to some extent, there is also some quantum information work to be done. So that's why I think that there is, one should never see this as a unidirectional process, but there is very likely something to be learned in both ways, that formulating the question in nuclear physics, go to the quantum info side, try to understand where there are the proper measures or witnesses, and then go back and study the phenomenon that one is initially interested in. So I think it's a kind of a loop, but I know too little nuclear physics to speculate further.
Excellent, but you answered it perfectly.
Alex, I can give you an example from the nuclear physics world, and it's not quite my work. This is again Seattle's work. But there was an interesting feature that we actually saw in our lattice QCD calculations of nuclear and hypernuclear forces. We saw kind of an accidental SU16 symmetry in the forces, which is kind of very similar to the SU4 symmetry of the nucleon-nucleon sector. And it was kind of interesting, and it's kind of, to some extent, is described by large NC, but large NC describes kind of a spin flavor symmetry, which is SU6. There has to be kind of this more parametric or accidental extension of the symmetry that we saw from this heavy pion mass kind of calculations. So then the question is that, is there any other organizational principle that could help us understand why these symmetries arise, right? Large NC is one of them. Heavy quark effective theory is one of them. And we have various different effective field theories. And the question was that, can entanglement also be a measure of kind of characterizing this kind of why these features exist? And in this very interesting work, in fact, Savage, Kaplan, Colloy, and Bean, they look at a quantity that is called entangling power of the S matrix. So again, coming back to Marcello's point, we have to be careful about how to define this entanglements now. What are these entanglement measures in systems that are more complicated in the scattering of two composite objects? How do we define these measures? But anyway, this particular quantity turned out to be very useful to look at. And what they see is that kind of the principle of entanglement suppression seems to be aligned with this, where these symmetries actually happen. This SU16 symmetry kind of is aligned with that principle. So then you start to ask, kind of, this conjecture, is it true, right? Why is that? Can we start to bring in and look at other interesting observables in nuclear physics by looking at things like entangling power of S matrix or other quantities, and learn something that we didn't know before? Is the question of, is entanglement more fundamental than other things that we have been considering, like large NC limits and things like that? So I think this is very interesting. And as I said, people have started to look into clever ways of taking advantage of this to uncover things about nuclear systems.
Excellent.
Yeah, thank you. I mean, one question that sort of comes to mind in this context is, you know, if I look at the phase transition or quantum phase transition, right? What's happening to the entanglement? And you know, of course, if we have some sort of length scale that's diverging, then that should probably be somehow be visible in the entanglement measure that we define. And I think then, at least to me, one of the questions is, how would we actually measure entanglement? I mean, of course, from a quantum information science perspective, defining entanglement or entanglement measures is really interesting. But then, is this really a good quantity from an experimental viewpoint in terms of quantifying theories? And I don't know if anybody has any thoughts on this, and you know, especially maybe also invite Mark and Paivi, who sort of had a bit more of a condensed matter view in their talks, if there are any insights that they might want to contribute to this.
Sorry, can you actually repeat the question? What was it? Different measure of what?
Well, I was just very broadly posing the question, you know, if we want to use entanglement or some, you know, entanglement derivative, some sort of quantity that might be appropriate for a nuclear system, for a high energy system. You know, and that turns out, say, to be a very useful concept theoretically. How do we actually measure it experimentally? So how do we, you know, how do we sort of connect the theory and the experimental world, right? Because if we do transport measurements, at least to the best of my knowledge, that might not necessarily reveal anything about entanglement, right? So you have to sort of, these measurements are not particularly trivial. But
yeah,
there has been progress made on the condensed matter side. So I wonder if there are any insights from that angle.
yeah. I don't know. There are, of course, really beautiful experiments from Markus Greiner's group on measuring entanglement. But they have a technique at use which I think is not available for nuclear physics. So basically, they have this quantum gas microscope. They have like a 2D sheet of atoms pinned into lattice sites, and of course the atoms can also tunnel. And then they can measure snapshots of densities of atoms at different sites. And since one snapshot is like one realization of the quantum system, if they gather many of them, they also get correlations. And then they have extracted from those really entanglement, and they can see different types of entanglement and so on. But this is really like looking at the densities microscopically with quantum fluctuations, and I think this is impossible in nuclear physics. Other than this, I really don't know, because it's always, I mean, it's often kind of hidden in the observables.
Were the sheets how they did it, or were the sheets necessary for doing it?
It's such a, if it's 2D gas, it's easier to observe one atom at a time. It could be also a 3D system, but then it's very hard to see where each atom is. And yeah, if it's a 2D sheet, you just shine light through and you see how many atoms was here and here and here.
So in principle, there could be like a 3D in the future experiment.
Yeah. So basically, if you would manage to see the positions of particle in 3D, and it's also important that you have like one realization of the system measured at the time, and not like average measurement, because that kills the correlations, usually fluctuations.
Any other thoughts, or, you know, if people just want to open sort of or pose open questions, I think that would also be useful, right? We're not going to answer, you know, all our pressing questions today, but I think if there are questions that sort of point out connections between the fields, that would also be just very useful to just articulate and Joachim, do you have something?
Maybe I can provide a bit of anecdotal information since I've been involved in calculating entanglement entropy at unitarity. This was already a few years back, and we together with one of my students, we developed a quantum Monte Carlo method to calculate the so-called Rene entanglement entropy as a measure of entanglement for quantum many-body systems, and this was at a time when I guess it was a couple of years delayed relative to what one might think was the sort of the big hype or the big start of understanding entanglement and scaling of the Rene entanglement entropy in condensed matter. And our experience was that these were very, very difficult calculations in 3 spatial dimensions. You don't just set up your quantum Monte Carlo as usual and calculate a different observable. It's actually a different type of calculation. The probability measure that uses different. We realized this, and that made it very, very challenging. It's similar in a way in QCD as when you want in QCD to calculate the pressure. That is, you need to calculate an equation of state first and then integrate relative to the chemical potential or some variable afterwards. So you need a lot of simulations, and then you integrate after that, and you get that entanglement entropy. But the connection that I wanted to mention that's anecdotal is that speaking with people at Oak Ridge, and it was not Thomas Pappenberg, it was somebody else. I forget exactly who he was. I think it was David Dean, maybe. And he suggested that instead of calculating the entanglement entropy in a spatial basis in coordinate space, so we could calculate it in, I guess that would be one could say particle number space, or rather calculate the entanglement not of the so-called reduced density matrix. So let me back a little bit up and unpack this. So to calculate the entanglement entropy, you need access to the so-called reduced density matrix. Is the density matrix of a subsystem of your full system, and but you may very well calculate the entanglement encoded not in that not in that subsystem, not in that reduced density matrix, but rather in the density matrix itself. So I guess you could think of it this way: if you have a system of let's say 100 nucleons, you can calculate the 2, 3, 4 body density matrix, and you can explore how entanglement evolves as a function of particle number as you make the system larger, that subsystem larger and larger. And I think they explored. So David Dean and colleagues, I think they explored something in that direction, but I didn't follow those studies. But I'd say that's potentially interesting in nuclear systems when you have a finite number of nucleons and you want to see how structure evolves when you look at the reduced density matrix with few nucleons at a time. That's my 5 cents.
Okay. Yeah, I think that sounds promising and interesting. And I think one of the things that, again, is sort of a question in nuclei, if you really have finite systems, could you possibly probe some of this physics in dedicated scattering experiments or in sort of dedicated, I'm thinking about neutron scattering or some sort of experiment like this. So I don't know the answer. I'm just sort of, brainstorming a little bit.
I think a quick comment would be that we should be careful that kind of entanglement entropy in some of these measures are not quite physical observables in a sense that they could be representation dependent, right? And one example of this, you mentioned this quantum phase transition or phase transition in general, right? So one measure of entanglement that you define might actually blow up, which shows some singularities. And I think in my view, I think it's just kind of a very rough understanding of what was happening is that kind of, it just tells you that the kind of representation or bases that you're picking to describe your system might not be the right one anymore, right? If you're kind of in a quark gluon plasma as opposed to a hadronic phase, in a hadronic phase, in kind of low energy effective field theory description in terms of the hadrons, there's a more efficient basis for representing that system, can kind of strip away a lot of the complexities of the underlying quark and gluon interactions, right? But on the other phase, it's not the right description, right? Not the right basis to capture kind of the physics. So I think in that sense, kind of thinking about these entanglement measures might also be kind of a way of signaling that the effective degrees of freedom are changing, right, in the system. And it's not a physical observable, but it's a quantity that can tell us about the efficient representation of the quantum degrees of freedom in the system.
I think this touches on several points that were made earlier, right? Like Joaquin has worked on this transition from few to many, and I think maybe that's what Marcello was also talking about, right? So clearly the degrees of freedom start to be different, right? Yeah.
I think, yeah, that's just an example. I said, once you have the physics, then there are multiple ways you can try to utilize entanglement for. And maybe since the phenomenology is different, you have to come up with different type of measures or witnesses, or maybe entanglement is just not the correct quantum correlation. You should look at Discord or Bell correlations, which are more complicated. So I think that there is a rich panorama and one has to go and try.
Something more universal, right? Some measure that is kind of...
Well, I mean, universal is a tricky word. I mean, if you think about quantum field theory, essentially only entanglement has been shown to have some universal properties. Yeah, think about both gauge and conformal.
Right.
But since here the phenomena are different also, I mean, you start about bound states and finite, I mean, maybe there is a richer playground. I am sure there is richer playground. Yeah?
Yeah, so given that we do, oh, Thomas, please.
Yeah, I wanted just to add to it, for the nuclear physics also, questions about correlation and entanglement are really resolution scale dependent, right? So some people search for short range correlations with and use a, not only a high energy probe, but a high resolution description and report about certain short correlations. But then people who use low momentum interactions and two-body current as corrections find the same results with relatively uncorrelated wave functions. So in that sense, I think this echoes about that probably entanglement is not really, it's a Hamiltonian or model or a resolution scale at least dependent quantity to look at.
Yeah, I mean, I think entanglement by definition, right? You say you entangle this with this, and you actually have the freedom to define what is this and what is this. And this is, I think, where our physics understanding comes in. I mean, what we want to choose is, at least from a very naive perspective, we want to choose a measure that really captures the physics that's going on, on this end and on this end. And then in between, we have sort of, generally speaking, a soup where things transition from one state to another, right? But the soup is also interesting. And how do we get insight into that? Is that via symmetries? Is that via an effective picture? Is that via, something blowing up? And that's the best insight that we can gain. Hopefully we can do better than it's just something blowing up. But I think that's sort of, right, intuitively, it's clear that entanglement, that's just the word, and we have to fill it with meaning.
In nuclear physics, if I may offer an example, which is not a near-term one, right? But if somebody could, from an ab initio perspective, describe a neutron star crust as containing both nuclei and matter outside, right? You already have a, kind of a spatial separation, right? You have the lattice of ions and you have the infinite matter. But of course, you have pairing in the matter and you have pairing inside the nuclei themselves. So, this seems kind of a natural application, sandbox for these ideas. But that being said, somebody would have to first self-consistently describe the neutron star crust before you could look at the entanglement and entropy or whatever properties. But anyway, just my 2 cents. Yeah. We have exceeded the 30 minutes, but I don't want to shut down the conversation, right? So it's a delicate balancing act.
But I was also just gonna say we do have 2 more days of talks. We have 2 more days of discussions. And so my suggestion is that we reconvene tomorrow at 3 p.m. Rome time.